by people coming in. No, not by students, by people coming in. Roots of complex numbers. There's the learning goal, success criteria. Now we're going to apply de Moivre's theorem to roots. So what I was just saying was, with a question like this in the past, you may have done something like this. Let that equal a plus bi. We know that the root of a complex number is always just another complex number. And then said something like negative 4 root 2 plus 4 root, that's not what I'm saying, 4 root 2 I is equal to a plus bi cubed. And then cube this out, and then equate your real component and your imaginary component, solve those simultaneous equations. For a cubic, it gets pretty out of hand pretty quickly, and it's quite hard to solve. And if we went beyond cubics, it would be even harder. So this process becomes unreasonable. Even with squares, it's quite an unreasonable process. The good news is that we can do this using de Moivre's theorem for any count quite easily. So let's run through this example. And I've got my steps here. Convert to polar form, use de Moivre's theorem, and then simplify, maybe put it back in the depending on what the question's asking. So how do I put this in the polar form? Into cis notation. What's that? Find R. What's R? R is equal to the magnitude, so we say the square root of negative 4 root 2 squared plus 4 root 2 squared, yeah? That's equal to the square root of 16 times 2, which is 32, plus 16 times 2, which is 32. So thankfully, that's the square root of 64, which we hopefully all agree is 8. Nah. What does it equal?
8.1 minus 1.
I'm just going to go with 8. Okay. I did hear somebody call out, no, it's a cube root, so just that's a good point. But we're just finding this in polar form, and then we're going to apply the cube root to that thing in polar form. Theta is equal to tan inverse. Remember that procedure for this, and you can look in your textbook. Our procedure for this is we can use sine and cos if we want to. That's just part of a triangle, and we're trying to find the angle theta for where that is on a unit circle. You right there, Connor? So that's what we're doing here. I use tan inverse, and then I just make sure that I'm being quadrant aware. So in terms of quadrant aware, if I sketch this, it's in the negative part of my real axis and the positive part of my imaginary axis, so it's in the second quadrant. So I'm looking for an answer to my second quadrant, but I get tan inverse of negative 4 root 2 over 4 root 2. Oh, sorry, that should be the other way around. It should be 4 root 2 over negative 4 root 2. It's B over A. Tan inverse of negative 1, which is negative 45, but negative, of course, is in the fourth quadrant. I want to be in the second quadrant. So what do I do with tan? Just add or subtract 180. In this case, we're going to add 180. So this is quadrant, that's just moved on me. That's quadrant 4. I'm going to add 180 to get 135 in quadrant 2. So this is equal to the cube root of 8 cis 135 or pi on, so 3 pi on 4. In fact, let's stick with radians where we can. And of course, the cube root can be written like this. To the power of a third. And how do I apply the power of a third using de Moivre's theorem?
You know what?
I'm hearing a lot of things and I'm just writing stuff down. Okay, that's what Connor said. And this is equal to 2. How's that look? That's a cube root. Now, something really interesting has happened when we introduce complex numbers. First of all, when you solve quadratics in year 10, sometimes you got 2 answers, sometimes you got 1 answer, sometimes you got no answer. As soon as we introduce complex numbers, as soon as we introduce complex numbers, we always got 2 answers. Complex numbers allowed us to always find two answers. There's always two solutions to a quadratic. Sometimes those two solutions are complex. So this is the problem we're dealing with now. That's a quadratic. This is kind of like taking the cube root. There should be three solutions. This is where we now need to be a bit more clever about applying De Moivre's theorem. There are three solutions to this cubic, or this cube root function. Does anybody have any suggestions about where the other one might be?
When they're back into Cartesian, so plus minus.
Quickly. I'm just going to plot this on an Argand diagram, and then we're going to do the next section. So our original function was out here. It was 8, so the magnitude of 8, and that was 3 pi. And when we took the cube root, we got a magnitude of 2, and the angle, that's probably not the right place to put that really. The angle is pi on 4, and the magnitude was 2. So it's come in, we've taken a third of the angle, it's come into there, and we've cube root as our length. Can somebody do this quick calculation of 2 cis 11 pi on 12 cubed? Assuming that 11 pi on 12 is all right. Don't have to do it in a calculator, you can just 8, somebody said? What's that number? 33 pi on 12, do we agree? Okay, what's 8 cis 33 pi on 12? How can we simplify that? Is it 135 degrees? Oh, so 24 pi on 4 is 2 pi. We can take that out, can't we? So we get 8 cis, if we take out 24, we'll have 9 pi on 12. And that's equal to 8 cis 3 pi on 4. So this thing cubed is equal to that. So therefore, the cube root of 8 cis 3 pi on 4 is equal to 2 cis 11 pi on 12. But 11 pi on 12 is here. No, it's not. That's wrong. It's over here. That's 2, and that angle is this angle here is 11 pi and 12. So we've got a second solution. And how many solutions did we suggest there were? 3. There's going to be another one down here somewhere. How do we find those solutions? Not quite. Let's have a look. Here's a generalization. The nth root of a complex number a plus bi is equal to a plus bi to the power of 1 over n. A plus bi can be written as r cis theta, so it's the nth root, or r cis theta of 1 over n, which is obviously that, so you've seen that. This is the trick here. I've just taken 24 pi over 12 out, Dylan suggested it, and that's what lined it back up with being in the right quadrant, or the right 0 to 360 for us to work with. So when we're solving this, we could actually have additional 2 pi factors inside my angle. Now that would take us beyond the 360 degree mark initially, but when you take a third of that value, back inside that 360 mark. That's how we're going to solve these questions, and this is going to be a generalized form. We could add 2 pi on, we could add 4 pi on if k is 2, we could add 6 pi on, 8 pi, 10 pi. At some point we've got to stop because k could be any number, and we know where to stop because it's a cube root, we're expecting 3 solutions. So we just do it twice, we get the extra 2 solutions. So we're going to run through this in a second. This is the simple view, this is the more complex view. That's example 2, but how about, no, let's just do example 2, and I could finish example 1 another time if need be. So you might want to write that down, you can write that down later, but I'm going to show you how to find the cube root of example 2. It's a little bit simpler, where the cube roots lie, and I'll show you on our Gann diagram what they look like, and we can go from there. Is it a bit simpler? What's the magnitude there? It's not very nice at all, actually. That'll be fine. So if we're going to take the cube root of something, or the nth root of something, we start by finding it in cis notation, Xander. And so to do that, r is equal to the square root of -1 squared plus 1 squared, which is equal to the square root of 2. And theta in this case is equal to tan inverse of b on a, which is 1 on -1. And that's equal to pi on 4. But we have to be quadrant aware. And I think I put this in the second quadrant again, haven't I? Which is there. So it's actually 3 pi on 4 again. So, and that's in the second quadrant. That's what we're looking for. I should say negative pi on 4, you're right. That should be negative pi on 4. That's what would come out of your calculator in the fourth quadrant. But we have to be quadrant aware and make sure we get into the right quadrant. And so therefore, this will be equal to the root 2. Actually, I'm going to write it like this. 2 to the power of a half, cis 3 pi on 4 to the power of a third. I do that power, I get 2 to the power of a sixth, which is not nice, but that's all right. Not cos, it's cis. And this is pi on 4. So I've just taken that third in here. That becomes 2 to the power of a sixth. And this becomes cis of, we do a third of that angle to get pi on 4. But what I actually have to do is take a step back and realise that I could add 2 pi factors in here. So I could actually have 3 solutions. So this is, so what I'm going to actually change this. My apologies. I'm going to write this down as 2 to the power of a half, cis 3 pi on 4 plus 2 pi k. This is my generalised solution now. So I'm going to do that to the power of a third. This is the step, the mystery step that we were missing before, and we're going to have 3 cases for 3 different answers. 2 pi k, any additional rotations around the Argand diagram will bring me back into the same location. So I'm going to start with, if k is equal to 0, I get my first solution, which I'll just call Z1. Well, actually, maybe I'll call it Z0. And that becomes 2 to the power of a sixth, cis pi on 4. That's my first solution. If k is equal to 1, I get Z1, and that's 2 to the power of a sixth, cis pi on 4 plus 2 pi on 3 times 1. So I've done that third times 2 pi k, but k is 1. Are we happy with that? And that's equal to 2 to the power of a sixth, cis pi on 4 plus 2 pi on 3 is 3 pi on 12 plus 8 pi on 12. That's 11 pi on 12, which is the answer we were looking at before. And then if k is equal to 2, I get Z2 is equal to 2 to the power of a sixth, cis pi on 4 plus 2 pi on 3 times 2. And that's 4 pi on 3. 4 pi on 3 is 16 pi on 12. Plus 3 pi on 12 is 19 pi on 12. So I get 2, 6, cis 19 pi on 12. And if I did this again for k equals 3, I would get 6 pi on 3 here plus pi on 4, which would give me in total that 3 pi on 12, 6 pi on 3 would be 18 pi, no, 24 pi on 12, so it'd be 27 pi on 12, which would simplify down to cis pi on 4. So we'd end up going back to the first answer. Chris. Yep, and the power of a seventh will always have 7 solutions. And it goes as well for if it was to the power of 2 sevenths. You'd still get 7 solutions, but you've got a square of that cis notation. No, because I got criticised for saying that. No. I've changed my ways to avoid criticism. And on an Argand diagram, they look like this. 2 to the power of 1/6 cis pi and 4, and 2 to the power of 1/6 cis pi and 12, and 2 to the power of 1/6, 19 pi and 12, so 11 pi and 12 for that one there. 19 pi and 12 is a little bit beyond 270 degrees, so it's there. That's pi on 4. This is pi on 12. That's pi on 12. They're the locations. And you should know here, if you drew this out with degrees, it'll be simpler for you to see. Each of these gaps will be 120 degrees. It'll be perfectly symmetrical, rotationally symmetrical around your Argand diagram, all with the same length to the power of 6. To the power of 6 and 2 to the power of 6. Any questions? I think I've talked to you probably enough. For now, I'll probably just do the rest on Wednesday. That's not what I wanted.